Hello everyone, good morning. Thank you for coming to this first session on the last day for the CHES conference. This is a session on quantum cryptanalysis. We will have 3 talks today. And the first talk is about quantum security analysis of module LWE. And the speaker is Sang-Min.
Good morning, everyone. I'm Sang-Min Cho. I'm from Hanyang University, and now I'm working at the E3 in South Korea. Today, I will talk about our paper entitled Quantum Security Analysis of Module LW PQC based on practical cost estimates. The outline of my presentation is shown here in the slide. The quantum computers pose a major threat to classical public cryptography. Shor's algorithm breaks RSA and ECC in polynomial time. To address this, NIST initiated the PQC standardization process. Since 2022, NIST has selected 4 algorithms as PQC standards: MLChem and MLDSA, SLHDSA, and FNDSA, with HQC added in 2025. MLChem and MLDSA are constructed based on the hardness of the module learning with errors problem, MLWE. The LWE problem involves finding a secret vector in a linear equation with noise, which reduces to the shortest vector problem, SVP. In other words, the reduction from MLWE to SVP means that the hardness of SVP essentially defines the security of MLChem and MLDSA. Therefore, accurately estimating the cost of solving PQC, cost of solving SVP is crucial for assessing the security of module lattice-based PQC. Previous works attempted to apply quantum algorithms such as Grover's algorithm to sieving. However, they only analyzed the query complexity, that is, the number of oracle calls, without providing quantum circuit designs, resource estimates such as gate count or depth, or accounting for the cost of quantum error correction. Our work addresses these gaps. Let's briefly recall the structure of a lattice. A lattice is a set of points in a multidimensional space that are generated by integer combinations of basis vectors. In cryptography, we use full-length lattices where the dimension of a lattice is equal to the rank of lattice. The shortest vector problem is to find the shortest non-zero vector in a lattice. Astai showed that this is NP-hard in worst case. This problem underlies the security of MLWE-based PQC. For MLChem and MLDSA, the underlying problem is module LWE. Given samples A and B, where B is equal to A transpose times S plus E, the task is to distinguish them from uniform. This reduces to solving SVP in a related lattice lambda. The best known approach is BKG with an SVP oracle. To solve SVP, sieving is the most efficient known algorithm for high dimensions. Classical sieving has complexity of around 2 to the 0.415 n, with the search step alone costing of 2 to the 0.206 n. This search step is where Grover's algorithm can potentially provide quantum speedups. Quantum computation leverages qubits in superposition, enabling exponential state representation. Universal computation requires both Clifford and non-Clifford gates. In particular, the T-gate is crucial but also under error correction, but also costly under error correction. We also use Q-AND gates, which reduce T-depths compared to the Toffoli gates. Grover's algorithm provides a quadratic speedup for unstructured search problems. It requires a custom oracle to mark solutions and a diffusion operator to amplify them. This is central to our quantum safe design. In reality, quantum gates suffer from high error rates. The surface code is the leading quantum error correction scheme, encoding one logical qubit into hundreds of physical qubits. Non-Clifford gates, especially T-gates, are implemented using magic state distillation, which dominates the cost of fault-tolerant computation. Classical operation for quantum error correction is time-consuming when performs quantum circuits in quantum computers. Full sieving cannot be directly accelerated by quantum algorithms. Only the search step benefits from Grover's algorithm. Therefore, we propose a quantum classical hybrid model. The classical part samples lattice vectors, performs reductions, and compares the vectors in a list. The quantum part searches for vectors that satisfy this condition. Our basic oracle OQS is built using quantum errors, squarers, and comparators. It negates the amplitude of states that satisfy the sieving condition. This design enables Grover's amplification of valid vector W. To compare the quantum state with the classical value, we designed the quantum classical subtractor. A carryover bit signals whether the condition is satisfied, triggering a conditional phase flip. The naive design has depths proportional to 6 times n. To reduce this, we parallelize quantum squaring operations using ancillar quantum registers. The optimized oracle reduces depths to 2 times n plus 2 at the cost of increased width. This trade-off significantly reduces QEC cost. We evaluate both versions of the oracle using matrix dw is equal to depth times width, and d square w is equal to depth square times width. These capture trade-offs between circuit parallelism and depth constraints. We provide resource counts for both OQS and OQS depth opt, including gate counts, depths, and T count. This is the first estimate of the actual quantum resource requirements for a quantum classical hybrid sieve attack targeting the parameters of MLChem and MLDSA. Using Qiskit, we validated our oracle circuit design, and the simulation results confirm that only the correct solution states are amplified, showing that our design works as intended. Next, we applied our circuit-level resource estimates to analyze the security of MLChem and MLDSA. We compared our results with prior NV-sieve circuits compared to Kim et al.'s circuit. T-depth was somewhat higher, but width was lower, and both T-depth times width and T-depth square times width were reduced. We adopt NIST's notion of max depths, representing plausible limits for quantum circuit execution depths. The concept of max depths relates to NIST evaluation of quantum attack complexity against PQC by assessing how many quantum gates are used at realistic depths. We also compute G-cost, which means gate count for the parameter sets of MLChem and MLDSA. These values are somewhat higher than the figures defined by NIST for each security level. Since, since T-gates dominate cost under QEC, we adopt the Reed-Miller 15-to-1 distillation scheme. We estimate the number of magic states, the distillation layers, and total overhead. This provides a realistic estimate of fault-tolerant quantum attacks. Our results show that quantum sieving reduces the security of MLChem and MLDSA by 15 to 27 bits compared to classical sieving. However, they remain above the NIST-defined thresholds. In short, MLChem and MLDSA are not broken, but their margins of security are slightly reduced in quantum computing environment. To conclude, we designed practical quantum circuit for, for the search step of lattice sieving, and we provided detailed gate-level resource estimates. And we also incorporated QEC-aware cost analysis, including magic state distillation. Applying this to MLChem and MLDSA, we found a reduction of 15 to 27 bits in security, but no fundamental break. Thank you for your attention, and I will be happy to take questions.
Thank you. So we have a lot of time for questions. Are there any in the audience right now? There's one question here. There's two questions, actually. Please.
Okay, yes. Okay, thanks for the talk. I was wondering, you chose Reed-Muller 15-to-1 as error correction codes. How large is the impact of codes with respect to the attack? I mean, if you would change with another code, would it get much better, or it's substantially that one?
For precise, Reed-Miller 15-to-1 distillation is for the magic state distillation in the quantum error correcting codes, and we apply the basic and popular distillation code, and we can accelerate the QEC with the better distillation scheme or others. Yeah.
The question was how large an impact you think it would make to change a code, or it's essentially close?
We computed the complexity of quantum error correction and the amount of operations for Reed-Miller distillation is sorry, I didn't compute the power of Reed-Miller distillation, but I will see the power, and if you email to me, and I will let you know.
Thank you very much.
There was another question, maybe two other ones.
Thank you for your nice talk. You just mentioned the MLDSA and MLCAM will lose some few bits of security under your quantum saving algorithms. So do you think in practice, these still can be seen as secure against the quantum attacks? Thank you.
In our analysis, according to our analysis, MLCAM and MLDSA are still secure in quantum computation environment, but the complexity of attacking the MLDSA and MLCAM is reduced compared to classical sieving. But our quantum sieve circuits are combined of many quantum arithmetic circuits, such as quantum adders, quantum classical adders, quantum squarers, and subtractors. So and there are many studies optimizing the quantum arithmetic circuits. So if the quantum arithmetic circuits used in our circuit is more optimized, then the quantum resources for our circuit can be reduced, and then the attack complexity can be reduced.
Okay, yeah. Thank you.
We still have a little time if there's another question. And if not, I might have one that possibly relates to the previous one. Okay, well, first, thank you for the nice talk. So my question would be, I understand that there's a lot of trade-offs in the design space for these quantum circuits. And maybe it's a naive question, but is it possible, or could it be possible to somewhat automatize this kind of design choices? Sorry. Would it be possible to somewhat automatize this kind of design choices in the different circuit style that you could have?
Yeah, we make the circuit by quantum modules as quantum arithmetic circuit as modules. So if the quantum arithmetic circuit is optimized, then the module is replaced by them.
Okay, I see. Yeah, okay, thank you. So we still have plenty of time, but I think we can thank the speaker and maybe go on to the next talk. Thank you again.
Thank you.
And for our second talk, we have new quantum cryptanalysis of binary elliptic curves. And sorry, but I didn't catch your name. It's
Kyungbae Chang.
Kyungbae will give the talk. Thank you.
First of all, thank you for your kind introduction. And good morning, everyone. I'm Kyungbae Chang from Hansung University, and I'm so happy to be here to present our work, new quantum cryptanalysis of binary elliptic curves. This talk is organized as follows. So let's begin with the introduction. Personally, I like this figure from Sam Jake, and this figure shows the quantum computing landscape in 2021 and 2024. So we can see the development of quantum computing over the 3 years in this figure. And this figure indicates the point where RSA can be broken. So in this light figure, we can see the recent work by Gidney for quantum attack on RSA. So she shows RSA can be broken with less than a million noise qubits. So this brings forward the point where RSA can be broken in this year. So this is what we want to say in our work. So actually, I just illustrated this a few days ago. So of course, this bound is not exact. However, I think binary CC might be broken earlier than RSA because implementing binary arithmetic on quantum circuit is much easier than such as factorization for RSA. This figure shows circuit for ECDRP, and in this figure, the most expensive operation is implementing multiple point additions as shown below. So for this quantum cryptanalysis, this algorithm is determined by the optimization of point addition implementations. So these three related works also focus on this optimization. Here are the basic quantum gates we use in this paper, and we can implement several Boolean functions such as NOT, XOR, and AND operations using this X gate, CNOT gate, and tuple gate. And let me present our contribution. So our main contribution is improving quantum cryptanalysis of binary elliptic curves. So because optimizing point addition circuits is crucial for this attack, so we optimize this point addition and we achieve the lowest circuit depths and an improvement of 73 to 92% in terms of depth times qubits product. And lastly, we simulate and analyze our short attack on binary CC with our circuits, and we evaluate its impact with post-quantum security standards by NIST. And this is our proposed quantum circuits. So for pointation over binary fields, we require the following arithmetic operations. So the question is, how can these operations can be optimized? So we call this component level. So actually, addition in binary field is just simple XOR operation, so we cannot complete in this area. So we just use CNOT gates to implement binary addition. And for scaling, we can represent this operation as linear layer like this. So this shows the squaring in binary fields, the modular reduction after the shifted result. So for input and squaring and repeated squarings, we can represent these operations with linear matrices. So for implementing, there are two main approaches. So first, in-place implementation using PLU factorization or linear optimization techniques presented in this good conference. And if we use this method, we can save qubits, but it increases circuit depth. And on the other hand, the second method, out-of-place implementation with a separate output. So in this case, we can reduce circuit depth, but we require extra qubits for output. In this work, we adopt out-of-place method. In contrast, previous works used in place. However, we will use output qubits for this implementation, and we can implement low depth squaring with an initial overhead, and I will talk about this later. And additionally, we propose and apply a compiler-friendly optimization in this work. So you can see the reduction in quantum depth after we applying this method. So if we approach in naive level, we will perform binary matrix multiplication by checking row by row or column by column. So In this case, some single qubit is accessed repeatedly. So in this case, we observe that this disrupts potential parallelization with other quantum gates. So in this case, quantum programming tools cannot find optimal deaths. So this shows our compiler-friendly implementation. We use diagonal traversal check, so it can avoid repeated access to qubits. So in this case, quantum programming tools can find the reduced steps like this, and we tested this phenomenon on various quantum programming tools such as Project Q, QSkit, QSharp, and CirQ. Then let's move to multiplication. So multiplication requires more quantum resources compared to squaring or addition. So we use Karatchev algorithm for here. And actually, 2 years ago, I proposed this Karatchev multiplication, and we adopt this in this work. So this multiplication has lowest circuit depth with a large number of ancilla qubits. However, we will use these ancilla qubits also, as in auto-place squaring, and it will be explained later. So we need to implement division also. So here we use Fermat's-Liller theorem. So we should combine multiplication and squaring here. So we call this combination level. So inversion based on Fermat's-Liller theorem should compute inverse as computing this exponentiation, and we can efficiently compute this combination using this Ito-Suji algorithm. This is our inversion circuit, and as we mentioned, we reuse output qubits for scaling with the reverse operation of scaling. However, this increases circuit depth. So to remove this overhead, we allocate 2 output resistors for scaling, and here one performs the reverse operation for the previous scaling, and the other performs next scaling in parallel. Thank you. So we can parallelize this reverse and normal operation, so we can reduce steps. So recall that we use this Karatchev multiplication, and the key advantage of this multiplication is the used ancilla qubits can be initialized with low cost. So we reuse only a single ancilla set, this one for multiple multiplications. And it is especially efficient for this kind of FFT-based inversion. As a result, our division circuit achieves 73 to 92% improvement in terms of this metric, depth times qubits product. Now, using these arithmetics, we can optimize point addition quantum circuits. So we call this architecture level. In this paper, we focus on affine coordinates point addition, as shown below, and we should note that in Schwar's algorithm, we should implement conditional point addition depending on the control qubit Q. So if the control qubit is 1, we should perform point addition, and the other case we don't perform point addition, so input is preserved. So this figure shows the point addition circuit presented in CHES. So you can see the result is computed in place on input depending on the control qubit. However, we found that this is not efficient for depth reduction because only a single control qubit Q is used for multiple controlled quantum gates. So in this case, all quantum gates controlled by control qubit Q are forced to operate sequentially, and it causes significant increases in circuit depth. So we propose new implementation copy, and in this circuit, the control qubit Q is copied, and record that our multiplication use many ancilla qubits, and these qubits in idle state. So we utilize these qubits for copying, and as a result, all quantum gates controlled by Q can be parallelized with its copies. We have one more improvement. So in previous implementations, one controlled constant addition and two controlled additions are performed. And in our new implementation, we only use one controlled addition, because actually this linear layer combination can be compressed in a single matrix. So we store all values in a single register and perform only one controlled addition, so we can reduce the complexity of this middle step. So our point addition circuit achieves 73 to 81% improvement in this metric. Additionally, we propose an out-of-place addition circuit in this paper. So in this circuit, regardless of the control qubit Q, we compute P3 while preserving the input. So in the final stage, the result is selected by the control qubit using controlled swap gates. So key advantage in here is we can reduce unnecessary operations in contrast to in-place point addition circuit. Yeah, so we reduce the complexity by about half, like this. So as a result, our point addition using out-of-place method achieves 92% improvement in this metric for single step. However, we need multiple point additions in short circuit, and if we use this method, we generate garbage qubits when we perform point addition. So actually, for now, I think this is not efficient for Shor's algorithm, but this shows the best performance for single point addition. So for estimating Shor's attack cost, we should calculate the quantum resources required for 2n plus 2 point additions in sequential. So we estimate the resources after decomposing duplicates in Clifford plus T level. And this is the result for our quantum attack. So in this table, we can see these full depths, and we should note that NIST introduced a parameter called max depth, and it defines the maximum quantum depth for feasible quantum attack. So we can see ECC can be our ECC attack satisfies this max depth, so we can perform this quantum attack. And this is another parameter, this post-quantum security level. For when in PQC document in 2016, NIST also suggested this post-quantum security criteria compared to AES. So we can compare the hardness of quantum attack with this standard AES, and unsurprisingly, ECs can be broken with much less quantum resources compared to AES. And this difference comes from the difference in algorithm levels between Schwartz attack and Goldberg's attack. So in this course, we calculate total quantum gates and full depths. In our paper, we use further improvement at algorithm level called windowing. So if we use windowed point addition, we use a quantum lookup table here. So we can reduce these point additions like this, depend on the window size. And please see our paper for more details. And finally, we compare our attack with RSA, and we compare the cost reported in this paper. However, actually, the most advanced paper for RSA is Gideon's attack this year. However, we just want to compare general quantum cost for implementing point addition versus modular exponentiation for RSA. So we chose this paper, and there is no optimization technique in algorithm level, such as windowing. So in this table, we can see our Schwartz attack on ECC requires much less quantum resources in all other metrics except for qubit count. So let me conclude this talk. To summarize, binary ECC is vulnerable to powerful quantum computers, and in this context, there are only few studies exist in this direction, and we found that only limited progress has been made since this CHES paper. So yeah, in this paper, we reduced the quantum resources required to break binary ECC, and we achieved lowest circuit depths and improvements in this metric. We should note that our work is based on simulation using quantum programming tool, not real quantum processor. So this is logical level analysis without physical constraints such as noise, decoherence, and error correction overhead. And I think considering these physical factors would be a recommended future work for us. That's all. So thank you for your attention.
Thank you. Are there any questions in the audience? I might have some questions then. I know that for curves, there are many kind of coordinate systems one can choose. And you said you choose the affine coordinate system. And I wonder if there are any particular reasons for that choice. And if, then, first of all, let's say.
Thank you for your question. As you mentioned, there are more coordinates, such as projective coordinates. And we tested that projective the coordinate, but we found that if we implement point addition circuit in that coordinate, we cannot construct in-place structure. So we need garbage qubits when we perform point additions. So we didn't choose that coordinates, and in other papers they also mentioned about this, and they just choose this affine coordinates.
I see, thank you. If there are still no questions, maybe, oh yes, there is one.
Thanks for the nice talk. My question was, you used Ito Tsuji as an inversion strategy. Did you consider other approaches, Euclid-based? There's one by Bernstein and Young, or it was just evident that Itotsuji was fastest?
Thank you for your question. As you mentioned, there is another technique for inversion, such as Euclidean algorithm, GCT-based inversion, and we recognize that technique. And however, that technique is good for optimizing cubic count rather than depth optimization, and we compared that performance. And I think for binary field, FLT-based inversion is much better than other options. Thank you.
Okay, thanks.
I see no other question, but I may have a last one. So you have optimized the circuit size depth for this particular work. Do you think it can be possible to go further? And if not, what would you say would be the next target if someone would like to further improve this quantum attack?
Sorry, could you please repeat?
So my question would be, what would be the next target if someone wanted to further improve this quantum attack against elliptic curve?
Yeah, thank you for your question. Actually, our work is heavily focuses on depth optimization rather than cubic count. And when I started this research, I just wanted to optimize circuit depth. And however, for now, I think qubit optimization is much more important than depth optimization, because our final goal is realizing quantum attack rather than reducing the runtime. So I think reducing the qubit count is recommended approach for future work.
Okay, thank you very much. Well, let's thank the speaker again. And we are going to have our third talk of the session with a little bit ahead of time. So. And this third talk will be about sieving with streaming memory access, and the speaker will be Ziyu.
Okay, so I think I have a lot of time, so I will introduce a little more about the background. Thanks for the introduction. So today I will first say something about the recent progress about the lattice attack, especially for the sieving method. And then I will talk about our work, the joint work with Jintai and Bo-Ying about how we deal with the memory access issue in large-scale sieving implementation. So after the, I think, 6 years post-quantum cryptography algorithms competition in 2022, the first 4 candidates were selected by NIST. The most recommended algorithm for general purpose usage may be the Crystal's Kyber and Crystal's DLSM. DLSM is a digital signature scheme and Kyber is a CAM. Both of them are based on certain lattice problem called the modular learning with arrow. And we also have Falcon, the highly compact digital signature scheme. So Falcon is, the security of Falcon is also based on lattice, the untrue lattice. So we can see among the first 4 candidates, only one is lattice-free, the Phoenix Plus. And luckily, this year, NIST also selected HQC, the code-based HQC, I think as a backup for Kyber. So from this, we can see, especially for the digital signature schemes, the lattice-based candidates are the most attractive. Because they achieve a very good balance between their signature size, their public key size, and signing and verification speed. And it enjoys the so-called strong provable security. Yes. So it's important to know the security of these lattice algorithms. We have mentioned that they are provable secure. So what is provable security? These security reductions only shows that if you can break these lattice schemes, then you are able to solve certain learning with error problem. And if you can solve LWE, you can then solve some approximate shortest vector problem. And I think we all believe SVP is hard. At least you should believe the exact SVP is hard. So this reduction says that it's hard to break these lattice-based candidates asymptotically. But the reductions usually has strict requirements on the parameters, and they are not often very tight. So they do not provide much meaningful guide for real-world applications. For the concrete parameter sets, they are always chosen according to the best-known practical attack. And here I want to say most cryptographic hard problems has been stable in the last decade, as long as it's not totally broken, of course. So for example, for the RSA factoring, the multivariate system solving and decoding, the improvements on the attack algorithms in the last decade, I think is something like 10 times or 100 times. Not too much, but the lattice-based cryptography is much, much less stable. And we can see here I collected some data from the Damastat SVP challenge and summarized it in the picture. We can see the green points use the enumeration complexity, which was the state of art in 2013, and the blue points use today's saving complexity. So the practical lattice stack are steadily growing in the last 12 years. And here I ignored all the constants because I only pay attention to the relative improvements. And I want to say it's not because that we are using much larger computational power. For example, in the last enumeration-based SVP record in 2018, it spent more than 1 year, I think, on a large CPU cluster, but the latest records, the 200-dimensional records, was done within 1 month on a single GPU server. Yeah, so, and here is another interesting example. It was estimated in 2010 that learning with error with parameters n equal to 256, q is about 4,000, and the sigma of the error is 8.35. At that time, took approximately about 2 to the 150 operations on the machine. And a single operation in enumeration, I think, is the 32-bit floating point operation should take more than 1,000 gates. So it was 160 bits at that time. But today, BKZ 300 and with block size 330, not the saving dimension 330, is sufficient for the attack. So it's about it's less than 120 bits today. In this example, we lost 40 bits in the last 15 years. Yes, much larger than the previous examples for RSA or multivariate. So what happened? First, there is a long line of work improving the asymptotical performance of lattice saving. Yes, from 2 to the power of 0.2415 to the 0.292. And here a natural question is, can we do better than 0.292 asymptotically? Luckily, it was shown that exponent less than it is impossible by better nearest neighborhood search strategy. So from the theoretical side, the story is clear. However, maybe a little bit surprising, these asymptotical improvements only contribute to a very small part in last decade's progress in SVP. The speed up ratio is less than 10 for sieving dimension 100. And the main reason sieving method is getting faster and faster is because it's hidden in the small n term. For example, we have the XOR popcorn trick, also known as SimHash. It performs a very quick check before the dot product computing, so much unnecessary dot products are saved. And we can also use the preprocessing or progressive sieving to largely reduce the initial vector length in the sieving database. And it's also possible to get some dimension for free by first sieving on a local projected lattice and then extend all the vectors to the full context. So after so many years improvements on the SVP algorithms, in a recent FAQ of NIST about Kyber 512, they said our best estimate for the gate cost of attacking Kyber 512 using known techniques is about 147 bits. So their minimum requirement was 143, so it's really in the edge of the security margin. However, this only means the gate count cost. In the sieving procedure, we need to deal with exponentially large sieving database of lattice vectors, and the memory access can be a serious issue in this case. So in the document, it also said combining the above estimates of the cost of memory access, the realistic cost of attacking Kyber 512 is equivalent to about 160 bits. So they think Kyber 512 is very safe. So does it make sense? The memory access can be a problem for the state-of-art sieving implementation at that time. Yeah, for example, if you want to solve the 200-dimensional SVP challenge, the sieving database will require about 10 terabytes of memory, so it's very expensive to put it in the system RAM. And even you can put it in the system RAM, the limited host device bandwidth will significantly hamper the BDGOC's practical performance, because if you want a very small bucket size, then you cannot achieve the peak performance for the graphic cards. So, and this issue is becoming more and more serious as the sieving dimension increase. And theoretically, the random access to an n-bit 3-dimension storage array costs cubic root of n, and if you are considering the 2-dimensional case, then it will be the square root of n. This is already clearly visible when n is very small. For example, I have collected some data from a textbook about the computer architectures, and you can see the most expensive computation operations, the 32-bit floating point multiplication, is cheaper than a single SRAM read. And the reading from the dynamic RAM is much, much more expensive. So what does our work do? This work suggests that the memory access cost can be negligible or minor in large-scale sieving attack, at least for the cryptography-related dimensions, that is about 400. So the inherent structure of BGJ sieve turns out to be much more memory efficient than the BDGO sieve with the state-of-art computation complexity. In particular, due to the 0.2028 stream memory access is enough. In practice, the stream memory access is much cheaper than the random access. And the time complexity, we also show that the time complexity of a modified BGJ sieve is very close to BDGL. At least in our implementation, it is faster for all practical dimensions we can achieve. So our work is also supported by implementation. The code is available, public available. And here are some performance results. We have implemented modified BGJ sieve and tested it with the SVP challenge. So no graphic card was used, but our result is much faster than the previous 42080 implementation. And if you look at the floating point operations, the ON term in our code is much smaller. Yeah, and we are using the cheaper 8-bit integer operations. Okay, let's first give a quick introduction to the sieving method. The sieving method is a natural generalization of Gauss algorithm for the two-dimensional SVP. So here I'm presenting a more practical version, which may attribute to the general sieve kernel paper. So during the algorithm, we maintain a list of lattice vectors, and we are always trying to find reducing pairs which generate new short vectors. Here, a reducing pair is a pair of lattice vector or a pair of list vector such that their sum or difference is short. So after the pairs are found, we can update the list by replacing the longest vectors by the new found short one. And the sieving procedure can be stopped when enough short lattice vectors are found. So it's very simple. And the cost of sieving is actually dominated by the search for reducing pairs. We have mentioned that there are sub-quadratic algorithms based on the locally sensitive filters for it. Yeah, actually, in the real sieving executions, almost all the vectors have the same length in the database, so it's just the nearest neighborhood search on a high-dimensional sphere. So the sieving algorithms based on locally sensitive filter usually has two steps. The first step is to put the list vectors into the bucket according to whether it can pass certain filters. And the pairwise quadratic search for reducing pairs is only happened within each small bucket. So we can save a lot of time, and the key point is that the reducing pairs are close to each other, so they are more likely to appear in the same buckets than a random pair. Okay, for example, in the fastest BDGO sieve, they use spherical cap shift filters. That is, a vector V can pass certain filters if the angle between this vector and the filter center is smaller than some threshold. So these vectors correspond to a spherical cap. And asymptotically, to choose to achieve the best performance, we should take the alpha to be about 0.5, and we will need 2 to the power of 0.292 such many buckets, and each of sub-exponential size. And if the bucket centers comes from random and it comes from totally random uniform distribution, and the bucket generation step will be unacceptably will be not acceptable. So the BDGO sieve use a random product code to choose the bucket centers, and the slowdown caused by the non-uniformity is well controlled. So what about the BGJ sieve? The strategy of BGJ sieve to reduce the bucket generation cost is very different from BDGO. It generates progressively smaller buckets by applying a series of random filters to the main database. And the pairwise search is only performed in the last layer of smallest buckets. So as the picture shows, one first applies different random filters to the main database and generate a list of buckets. And for each of these buckets, one can then run some random filters again and apply them only to the vectors within the bucket. So we get smaller and smaller buckets and only reducing in the last layer. As for the memory access cost, the key observation is that the bucket size decreases by several orders of magnitude after each filter. So this allows the sub-buckets to be stored in a much smaller and therefore faster storage device. And no communication between these sub-buckets is necessary. We only need to insert the short vectors we found to the main database. So, and the data movement is streamed except for the filtering stage. In the filtering stage, we don't know which buckets a vector will be put into until the dot product computation is done. So, but in all other places, the data movement can be streamed. And the observation is actually supported by implementation. Yes, in our current implementation, we use 3 layers of filters. And the profiling data for receiving dimension 140 is presented in the table. We can see the main database is about 300 gigabytes, and they are put in the system RAM together with the first layer of buckets after filter 0. So after the first few filters is done, the bucket size is finally smaller enough to fit in L3. And we can observe a significant speed up. And in the reducing step, the computation is even faster because we can put in even smaller and faster L2 cache. And the profiling data shows that most of the computations are happen when the bucket size are very small. So in these cases, the memory size cost will be minor. And what's the difference between the state of between BGJ sieve and the BDGL sieve? Yes, the BDGL use a single layer of filters to generate exponential many buckets all in one time. So in a straightforward, at least in a straightforward implementation, one has to write to the exponentially large space for these buckets. So you have to randomly access to exponential large memory. However, if in the BGC we use logarithmically many successive filter layers, the number of sub-buckets can be well controlled. It will be sub-exponential, and the practical value for it in our implementation is very small, only 100 for receiving dimension 140. So will this streamed memory access cost be a bottleneck for the BGJ sieve? Actually, for each bucket, including the main database, the computation happened with the computations required for the further operations in the bucket is superlinear in the bucket size. Yes, with the exponent range from 0.292 to with the exponent range from 1.4 to 2. Yes, the 1.4 is for the main receiving database and 2 for the quadratic naive search in the last layer of buckets. So the memory movement has exponents 4/3, so it's smaller than the computation. As long as the sub-bucket size is larger than some threshold, larger than some constant, the memory access overhead should be negligible. But when the bucket sizes are very small, in the last layer, several layers of the buckets, it's hard to estimate, but at least for the current computation architectures like GPUs or CPUs, it's not a problem as long as we take the bucket size not too small. Yes, something like 100 or 1000 will be well enough. But for a more serious attack using ASIC, it may be a problem. And this paper is actually written about 1.5 years ago. So following idea of this paper, an implementation of the BGJC, which put the main database in the on SSD, and computation happened on multi-GPUs was done several months ago. And now we are no longer restricted by the size of system RAM, so we can save on much larger saving dimension, and we can save much faster. Yes, I think now a saving dimension about 175 is possible within something like 1 month or 2 months on a single server. So we have used it to set some new lattice record, for example, the 200-dimensional thermostat SVP challenge. Okay, and that's all. Thank you.
Thank you. Are there any questions in the audience? We have a bit of time, so don't be scared. So I had a question. It just slept out my head for a second. I'm sorry. Give me a second. I will find it again. I'm sorry. Okay, I will ask another one that I also had. So, is there any concrete impact? So, I think you highlighted that there are some concrete impact on the bit security of the current scheme. Can you tell us a bit more about that?
The concrete security of the current lattice-based schemes. I think, at least as now, this lattice scheme should be secure. The exact number, Niels says that it's 147 or 145, but it may be a little bit error, but I think it will likely to fall in the range 140 to 150. So anyway, it's secure today, but as we can see, we lost so many in the last 12 years, this picture. So if you want so-called long-term security, for example, if you want to protect something for 50 years, those level 3 parameter sets are more recommended. At least I think it's more recommended rather than level 1.
Thank you. And my other question came back. So it's very nice that you provide also the implementation for everybody. I want to highlight this one more time. I had a question on this. Is there any plan to include this sieve style into other packages like FPLLL or FPyLLL, things like this?
Maybe a little bit hard. But the current implementation, you use command line. You just type some command line operations, and no need to call functions in libraries. So I think it will be okay.
I see. Well, that would be useful if we could have directly the whole process BKC plus sieving. But I see. Yes, thank you for your answer.
At least for smaller dimensions, our code will be cheaper to run.
I see. Okay. Thank you. I see no other questions, so let's thank the speaker again. And we are ahead of time, so I guess congratulations. Thank you all for attending this session, and let's have a last round of applause for the 3 speakers of the session.